Okay. Kia ora koutou. My name is Tim Sullivan, and it's my pleasure today to welcome you to a seminar that Professor Rajesh Dhakal is going to give us. Rajesh obtained his PhD in 2000 in Tokyo, Japan, and came to the University of Canterbury in 2003. He's a chartered professional engineer. He is a fellow of the Engineering New Zealand and the New Zealand Society of Earthquake Engineering, and he is editor of the Bulletin of the New Zealand Society of Earthquake Engineering. He's also on the board of the International Association for the Seismic Performance of Non-Structural Elements. The talk he's going to give us today looks very interesting. It's on beam elongation and the effects of beam elongation on RC frame buildings. And so it's a real pleasure for me to welcome Rajesh today, and I look forward to hearing this presentation. Thanks, Rajesh.
Thank you very much, Tim, and hello, kia ora, everyone here who are at this venue and who are online as well. So this topic we worked on since 2006 when I had a couple of postgraduate students, Adam Walker and Brian Peng, and since then we have continued on relevant areas of research. So as after the Canterbury earthquakes and also the QuakeCoRE earthquake, we have had several buildings whose damage had been linked with beam elongation or its side effects. I thought it is very timely for me to summarize the work that we have done in my research group, because I felt that some of the things that we have done has probably gone not been noticed as much. So let's see if I can give you a good summary of the things that we have done so far. So in this presentation, I'll outline the following things: causes and consequences of elongation, and how do we model elongation for analytical prediction of seismic performance of reinforced concrete, generally frame buildings, and the development of a new plastic hinge element for numerical prediction of elongation, experimental validation of that element that has been developed, and the application of it to ductile RC frame buildings with precast floors, and some of my thoughts on the ongoing discussions on the performance of reinforced concrete frame buildings, ductile buildings with typically New Zealand-based precast flooring systems. So the elongation of plastic hinges, those of you who are new to it, it is just a phenomenon where a member, a reinforced concrete member, ductile member, grows in length under inelastic cyclic flexural action. So for example, when a beam is subjected to, ductile beam is subjected to cyclic loading, and when it goes from one direction to the other direction inelastically, the reinforcing bars develop strain, and that strain, when it goes in tension, doesn't unload fully. So the center line of the beam shifts away from where it was in the previous cycle, so gradually developing that, accumulating that elongation, right? And there has been quite a bit of work in New Zealand on elongation, and we have been able to quantify it roughly, looking at all the test data and our understanding of elongation. We know that elongation is typically in the order of 2 to 5% of member depth, but it mainly depends on the level of axial force. So obviously you can imagine the axial force, if you have got compressive force, then your elongation will be smaller because it will not elongate as much. But if the axial force is tensile or that compression force is less, then you can get significant elongation. And the second thing that matters is the type of plastic hinges. And when I say that, we broadly divide the plastic hinges in two categories: unidirectional and reversing. And in unidirectional, which is typically in gravity-dominated frames or gravity-dominated buildings. It doesn't necessarily mean that the seismic demand should be low, but even if the seismic demand is reasonable, you use very high ductility factor to reduce the seismic design force, then the gravity action can become significant in comparison, and you will get hinging of negative and positive hinging at different locations. And when this frame now sways to the other direction, you can see the negative hinging forming close to the column interface and the positive hinging forming here. So you develop 4 hinges here, each of which will have yielding of reinforcing bars in only one side. Right? So there is no yielding in both sides. So you can gradually accumulate the rotation in this type of plastic hinge, which is what we call unidirectional plastic hinge. And ultimately, after a few cycles, you will get the idealization of this kind of plastic hinges will deform the beam like this, where you have got a sagging segment in the middle, and it can be modeled or it can be idealized as accumulated rotation in each of these 4 plastic hinges, which are unidirectional, yielding in only one side of it, right? So we know the mechanism, and the large inelastic strain in tension reinforcement develops when the rotation of that plastic hinge occurs. And on the compression side, it always comes back because it has not yielded any time during the cyclic loading. So although your tension keeps on increasing, your compression remains there. So in the mid section of your member, you will get an elongation, total elongation, which can be quantified by this simple formula, which takes into account the accumulation of rotation. And this was given by Richard Fennick and his research team back in the 90s. Now, the reversing plastic hinge is when you have got seismically dominated frame, where the seismic moment, or this, when you add the seismic moment, which is the symmetric straight inclined line here, on top of the gravity moment, which is the parabolic that you see compression or the negative moment on both ends. When you superpose that, you still get a slightly parabolic shape, but your maximum positive moment is here, maximum negative moment is here. So whether you develop or you sway it to the right or left, you will get the hinging at the same location. So at each location, you have got yielding of top bars as well as bottom bars, right? So both sides. And that means like the compression bars, when in the next cycle they have subjected to inelastic tensile strain, they don't come back fully. So in this case, like you can see the major difference because compared to the previous one now, you can see a permanent extension in compression reinforcement on top of what we saw in the unidirectional plastic hinge. So that is the distinct difference between these two. And this permanent extension in compression reinforcement mainly comes from 2 sources. Now let's look at this idealization here. So when a reinforced concrete ductile member is subjected to inelastic cyclic loading, then because of those inclined cracks in the 2 directions, you lose, you know, like the traditional mechanism of compression zone, because the cracks in each extreme of the cross section, which would have opened, wouldn't fully close. So that's why the concrete directly applying the compression isn't true. But there is another mechanism, which is the diagonal compression, diagonal shear mechanism, and this diagonal shear force will have its horizontal component. So if you look at the equilibrium of this cross section, there is a tension force carried by the reinforcing bars, there is a compression force carried by the reinforcing bars at another extreme, but that will, the difference between this C and T will be the horizontal component of that diagonal shear force, right? So the V divided by tan theta, the V is, sorry, this is a little bit annoying, I don't know how. Minimize this one. Yeah, thanks for that. So this, the shear force V will have its horizontal component, and that is the difference. And now let's look at this in a slightly different way. Let's look at the two bars, the bars at the top and at the bottom, right? So that is your equilibrium here. So a bar which was in compression in the previous cycle now gradually goes into tension and strain hardening towards strain hardening, because it needs to develop much larger force than what the compression bars need to develop, right? Whereas these bars which are going in compression would have already gone in tension in the previous cycle. And when they unload, they don't need to come back fully, because the amount of force they need to develop is much less than what the tensile force needs to develop. So for equilibrium also, like, because there is a residual strain in the middle, which keeps on increasing in each cycle. So that is mechanism number one. The second is actually when you have got a bar, when you have got a yielding on both sides. A yielding means your cracks are reasonably wide, and when that happens, the concrete particles that disintegrate and some of these small particles, they plug into the cracks, and when the unloading happens, because these small concrete particles, they act as the breeze and they don't let the crack fully close. So these two collectively, they provide that permanent extension in compression reinforcement. Why does elongation matter? So you all have seen this sway, right? So when a sway mechanism occurs, we idealize our system as this. But if this beam in the middle is getting longer, then that idealization is not true anymore. So you are now subjecting your columns to a larger drift. And when that happens, not only the drift, but also the internal actions, the shear forces, the bending moments, and axial forces, they all change. And without accounting for elongation, we cannot capture those, right? And the second thing that is that it matters is because it interacts with other elements. And two of the significant interactions that worry us is actually the increase in flexural strength of the beam. I will explain that in a while. And then it may also cause localized failures, such as because of the elongation. We all know the propensity or the probability, likelihood of unseating of precast floor units and falling off from their support, right? So accounting for elongation in practice, let's look at how it is dealt with in practice. So several reinforced concrete buildings damaged in Canterbury and QuakeCoRE earthquakes were attributed to elongation. I have given some example here. Clarendon Tower in Christchurch, Desbo's presentation, he has talked about this quite a bit in his different presentations. B&Z building, Statistics House, right? And significance of beam elongation is hence well acknowledged in New Zealand. I would say in New Zealand because I still have a fresh memory of a paper being submitted to an international, very renowned journal on beam elongation, and the editor returning back the paper saying that we have already dealt with this in the United States, so it is no longer a problem there, and not even sending for review. So obviously in New Zealand it has been well acknowledged, but I couldn't say the same for the rest of the world. So in New Zealand, we also added a requirement, check requirement for elongation in our recent amendment of the concrete code, NZS 3101, right? Nevertheless, the effect of elongation is generally overlooked in analysis. And mainly because, it is not because we don't acknowledge the importance, mainly because the traditional lumped plasticity approach, which is very commonly used to model and analyze reinforced concrete frame buildings, cannot capture elongation. And the second point I put there is traditional fiber model with cyclic path-dependent material stress-strain relationships, they can capture elongation, but they need to be cyclic path-dependent. The path dependency is the key, but this approach is not practical for analysis of large-scale structures, right? And in this research, part of this research, we have developed a plastic hinge element that can be used numerically to predict elongation, still in the traditional lumped plasticity setup. So that is the key, right? So we don't want researchers to go back to fiber model fully, which is not preferred for all types of analysis. It's still good for research. So plastic hinge element, what is it? The concept is that actually as in the lump plasticity approach, we use this plastic hinge element at the potential location of inelasticity or plasticity, and don't worry about where the plasticity would occur or not. Just put it on all the ends of all members, and if the demand doesn't reach the elastic limit, it will still remain elastic, right? But it allows it to go plastic when needed. And I've given some papers throughout the presentation where the details can be found. So it is basically a multi-spring element where we have got the concrete and steel springs, and these concrete and steel springs you can further divide into cover concrete and core concrete, and each of these springs can be modeled by using the generic reinforcing bar and concrete cyclic hysteresis models. So there is no calibration needed because these are standard material models that you use. You just multiply with the area that this spring is representing. And in order to capture the shear flexor axial interaction, we also provide the diagonal concrete compression string springs, which will take care of that diagonal shear that I explained to you earlier, right? Because without that, you wouldn't be able to capture the difference between compression and tension, and then the elongation is misrepresented. So unlike zero-length rotational springs used in traditional lumped plasticity modeling, the plastic hinge element has a finite length, right? So that is the key difference. Whereas in the lumped plasticity, you provide a zero-length rotational spring which never elongates, which doesn't leave there. Whereas here, this plastic hinge element can change its length, but initially the element has a sustained finite length, which is defined by how many stirrups are needed to engage, to balance the shear demand. So that is the theory that we use, which is not uncommon from the traditional truss theory for beams, right? And then advantages of this plastic hinge element, obviously we cannot highlight the advantage without looking at what are the issues with the conventional lump plasticity. Lump plasticity requires spring hysteresis to be calibrated in advance. You have to calibrate the moment and rotation at different milestones. Zero-length rotation springs force the members to always retain their length, not change their length, cannot cater for changes in axial load during analysis because you have to calibrate your model with the value of axial force for the moment rotation relationship, and unable to account for the following effects of elongation, which includes axial forces induced in members trying to elongate, additional exterior column drift demand, additional column yielding, changes in shear force and bending moment profile. So all these things cannot be captured. So obviously the advantage of this plastic hinge element is that it overcomes all of these and still allows you to do macro analysis, right, without too demanding fiber analysis for a large building. So let's come to the details of that element. Further details can be found in the papers that I have listed there. But let's go into some of the basic level of experimental verification. So first level of verification we did was with cyclic loading test of beams. And Adam Walker, my master's student, he did test a series of beams. And this is the test setup where we had exactly the same beam protruding cantilever in two sides of this support block and applying different levels of axial and cyclic lateral displacement, but these two beams were subjected to different loading regime to recreate reversing and unidirectional plastic hinge. So one was, like gradually subjected to larger rotation through unidirectional plastic hinge mechanism. The other was subjected to reversing plastic hinge mechanism, and we measured quite extensively all the deformation in the beams. And the model in Romoko, because that element was prepared, and then the subroutine was integrated in Romoko as a 1D element, and then we did this modeling where, as you can see, for this plastic hinge element, for the finite length, we replaced the elastic beam with that new plastic hinge element, and then you can apply the axial load as well as the cyclic displacement, and you can see the comparison between for one of the typical specimen, right? So when no axial force was applied, you could see the elongation being captured reasonably well. well. You can see general features of force displacement relationships, but what was not well captured was actually this pinching that we saw in the experimental result, because the analytical result was still buzzed out in the middle. And when we broke down the deformation into flexural deformation and shear deformation, we found that the flexural deformation was overestimated. Right? So although in terms of the force or capacity, it was showing good behavior, but in terms of deformation, sources of deformation, that was not the case. And we dug deeper and we found that the reason was because in the model, the shear deformation is not fully accounted for. And when we look at the shear deformation, we can break it down into two sources for shear deformation. The first source is when your beams or plastic hinge elongate and it is at the same time subjected to transverse displacement deformation, then the shear deformation must happen, right? So that shear deformation is affiliated or means is to be compatible with the elongating plastic hinge element, which is included in the model. But there is a second mechanism, which is the extension of stirrups. Right? So when you apply cyclic loading to a ductile member in the plastic hinge region, it might be difficult to comprehend at the beginning, but like the depth grows. Because your confining action and anti-blocking action of the reinforcement stirrups actually cause some of the stirrups to yield. And it was not easy to actually get evidence of that. And then when we started digging into experimental result, even in our experiment, Adam Walker, we measured the depth and even the strain in the stirrups, and we saw actually the depth growing quite substantially. Like that, you can see the depth of the beam near or at the plastic hinge is much larger than that. And when you look at the strain in the shear stirrups, the strain have already yielded. Okay, they have already yielded. So the contribution of the two mechanisms that I explained, which was one was the like the shear strain compatible or shear deformation compatible with elongation. The second was the shear deformation due to the extension of the stirrups. And when we compared the experimental findings with the findings of our own model or the prediction of our own model, we found a very good match with the 1 to 2 slope line. Means only half of the shear deformation was being captured. So we were forced to conclude that, okay, roughly the other mechanism that we are not capturing is equal to what we are capturing. So hence a factor was applied, a factor of 2 was applied to adjust the shear deformation. And once we did that, we could get a very good match, not just in terms of load displacement behavior and elongation, but also in terms of pinch to hysteresis loop, the breakdown between shear and flexural deformation. So all these things, details can be found in the paper listed below. And then not only that overall deformation history, but you can look at the evolution of deformation, right, or elongation. So at each cycle, ductility of 2 first cycle, ductility of 2 second cycle, similarly ductility 4, ductility 6, we measured through our extensive instrumentation, we measured the elongation of the member in the experiment, and in the analysis we captured that, and this is the comparison, which shows really good match in terms of the profile there, or evolution history, right? The comparison of results after all this, like when we collected many tests from literature as well as in addition to our own tests, then this is the match in terms of analytically predicted elongation with experimental elongation, beams with no axial force, and here is beams with axial force. So for all of them, this level of match in experimental statistical data set is perfectly acceptable. So then the next level of verification was with for a 2D frame, like this is a 2D frame. In Brian's thesis, you can find maybe 2-3 other verification as well, but this is the advanced one that we took from a test done by Wu at University of Auckland. So it is his thesis details the details of this test, but it is a 2-story 3-bay frame and with 4 columns, which was subjected to cyclic loading, and they measured the deformation of the beams and they also reported the elongation measurements. So that's why it was very conducive for our verification. So obviously, two different modeling approaches. If you had to model it using lumped plasticity, the conventional one, this is it, where each of these dots represent a rotational spring, right? So the lumped plasticity, whereas here our approach was to apply that plastic hinge element at those locations, right? So here, of course, you can apply this plastic hinge location on the column as well, at the end of the column. But here we were sure that it will never go into plasticity. That's why we didn't bother. So in terms of the load displacement curve, that was reasonably well captured with the analysis that we were doing. And you can see the prediction in terms of frame deformation. One unique thing that you can see is the deformation of this column, how much this node has moved away here and how much this has moved away. Similarly, when you go to the end, this movement is a lot longer than that movement. And that difference is the accumulation of the elongation of these plastic hinges of these three beams, right? Similarly, on the upper story as well. So that is captured by this analysis, whereas not by the traditional analysis. Induces axial forces in beams, right? So obviously, this beam is trying to get longer, and your column is trying to stop that. So obviously, despite having some elongation, but there is the restriction of towards the elongation by this column. So you will develop axial compression in these. Now you can imagine when the bottom is elongating more, the column is trying to deviate outside in the top. So the beam, despite trying to elongate, the elongation is not enough. It is trying to pull it in. So the tension force is developed on the upper story. And that is captured by the analysis, right? Additional column yielding, because of that extra deformation, the column yielding, which is additional, which wouldn't have been captured in the traditional analysis there. So here I'm showing the analytically predicted beam axial forces. Obviously, in experiment, the axial force on the beam wasn't measured, couldn't be measured, right? But in analysis, we can capture, and you can see bottom story, the compression force is being developed, right? And the top story, the tensile force is being developed, okay? And elongation history, like at each cycle in the analysis and in the experiment. So you can see in the experiment, the elongation is slightly less than, especially in the large inelastic cycle, slightly less than the analysis. As the experiments were not done by ourselves, we couldn't get to the depth of it, but reading the report, it was because that's when the buckling of the bars started happening. And when, you can imagine in the plastic hinge, when the bars buckle, the reason to elongate is less. So basically the elongation is kind of stagnant after that. Whereas in the analysis, as of now, the bar model with buckling actually was showing still some numerical instability. So this prediction is using a cyclic path dependent model without the causes of buckling. And when you look at the shear force diagram predicted in the frame due to conventional analysis and this novel analysis, you can clearly see the axial forces in the beams, like 5140 kilonewton in comparison with the very nominal values. And these additional values are all due to that elongation effect. And that alters your shear force in the column, because if you have got axial force in the beam, that has to participate in the joint equilibrium for the shear force. And you can see large shear force developing here, 77, right? And similarly, you can see similar effect in bending moment as well. The bending moment values are not captured properly without this element. And the final level of verification that I'm showing here is a 3D floor frame subassembly, which is what we tested in our old extension lab, those of you who are familiar with it, where the Jeff Matthews, Cameron McPherson, they did all these big tests. There was one further test of the same scale, which doesn't get the same attention normally. That is the Brian Payne's test. We have got 6.1 meter by 6.1 meter with a 3D frame floor subassembly. The details are given in that paper. These are some of the photos during the preparation of that specimen. So you can see and this is the instrumentation, right? So we were doing is actually we were testing it in the cyclic loading, and we were measuring all the deformation in the columns and beams here, and also on the floors, right? So to see the floor deformation and measure the cracks on the floor. And when we subjected to the loading, there was one challenge, because in this setup, like if the beams elongate and we fix the position of this bottom, then there will be additional axial force we are creating. Right, so we didn't want to stop the tendency of beams to elongate. That's why the displacement were iterated to ensure that the columns always remain parallel. So the bottom was actually two-way linear bearing, so that they could move in the direction that was needed to not restrain elongation, and the shear force is equal and opposite in each column. Right. So, and this was modeled using, again, in Ruamoko, using the plastic hinge element at the end of the beams. But the plastic hinge element, actually, we had a very preliminary version of 3D, because we had developed in 1D setting. But for this, we had to take into account the other direction as well. And all other elements were like cell elements to represent the floor slab, because it was precast rib and raft system. So beam elements to represent the pre-stressed rib, and then there were beam elements for your normal transverse and longitudinal beams. And this is the analytical and experimental load displacement relationship. So we'll come to that in more detail later, but let's look at some of these key findings here, right? So when you look at that specimen, there are two internal plastic hinges and two external plastic hinges. The internal plastic hinges are like restricting, because they are restricted because there is continuity of the specimen. So you can see the level of difference in the external plastic hinges, the level of damage, and internal plastic hinges level of damage. And this is in line with some of the observation that I had after the Canterbury earthquakes in some reinforced concrete frame buildings in Christchurch. And not only that, actually, you can see in the internal and external plastic hinge, the precast rib, the seating on the transverse beam, the opening of that, the tearing damage, the opening was a lot higher in the external plastic hinge, external edges, and much smaller, much restrained in the internal one. So clear message was the external plastic hinges will be subjected to greater demands or greater damage compared to the internal plastic hinges. And the axial forces in the internal plastic hinge and external plastic hinge. In the internal plastic hinge, much larger axial forces were developing. That's why the elongation in the internal plastic hinges obviously should be less, and let's see what the analysis shows, right? And in the external plastic hinges, the axial force developed was much smaller, so that indicates the relative values of plastic elongation. And here you can see these are experimentally measured elongation in plastic hinge 1 and 4, the external plastic hinges, and plastic hinge 2 and 3 in the internal plastic hinge. And analysis and experimental verification. So that difference between the two is captured by the analysis, but in terms of the value, analysis was slightly under predicting the overall deformation. So because it is a 3D setup with a lot of interaction, we still have to get to the depth of it, because there are other mechanisms that are not catered for in the analysis that might probably be contributing to it. So the further work needed on this space is incorporation of bar buckling and fatigue model in the plastic hinge element, which will enable us to estimate the residual life of RC frame buildings, one of the key issues that Ken and his team are dealing with at the moment. So this model can be really useful for that as well. Develop a 3D version of the plastic hinge element accounting for bidirectional interaction, which will enable microanalysis of torsionally sensitive RC buildings, and obviously incorporate this element in structural analysis programs, more widely used or open source program. Currently it is in a preliminary version in Ruamoko, but probably programs like OpenSeas will be good. So let me spend the last 2-3 minutes talking about like the interaction between the elongation and frame and the slab and the floor slab. So this is the subassembly that we tested and the experimental result. When you look at it, actually you can have a fair estimate of yield displacement and the ultimate displacement and these maximum forces. And when we compare that with the theoretical flexural strength by taking into account the beam strength, which comes out 192. So 333 means more than 60%, about 60% increase over strength. And even when we look at the over strength specified in New Zealand code and ACI code, it is well under what this subassembly is giving, right? So obviously the strength is much larger than looking at the over strength. The strength is much larger than what we are getting. So getting deeper into it, because we had measurements in the transverse beams as well as longitudinal beams and the floor slab, by doing a lot of simplification and coming up with some estimation, we found that there are three causes for that strength enhancement. The first one was the composite flange action, which is well known, like when you construct monolithically the slab and the beam, the slab will participate. You look at different codes give you different values of that equivalent width. It is usually a source of, not all of them can be right. If one is right, the other are wrong. So there is some uncertainty, which is problematic. And this roughly about 30% increase. And the torsional resistance of transverse beam, because there was monolithic connection with the end beam in the transverse direction, and when the form were deforming, because the force was transferring at the top of the transverse beam, so the beams were forced to rotate, and that rotational resistance was creating or giving this about 18% contribution. And the third was the beam elongation effect, the remaining, right? So in the beam elongation effect, like the beams forming the plastic hinges, we're trying to elongate, and the precast ribs, which were spanning in this direction, they were trying to confine it because they are stiff axially, right? So that creates maybe some axial force, and these axial forces actually enhance the beam strength much more than what you anticipate in your design, right? So that, because when you have axial compression, that does increase the flexural capacity. So these were the three mechanisms. So when we look at the frame-floor interaction, we can summarize the damage in three key aspects, right? So the first one is, because of that linking slab that we have and the beams trying to elongate here, the compatibility demand between the slab around the connection with the seismic beam, you get these shear cracks invariably. Okay, and then the crack width between the floor and the transverse beam interface, because this transverse beam, one here, and in the middle, like because the precast ribs are axially stiff, they avoid wide cracks in the floor slab body. So all the deformation to be compatible with the elongation will have to go into this interface with the transverse beam. So as I showed earlier, in the interior plastic hinges, that opening is much smaller, whereas exterior plastic hinges, that opening is large. And the third one is actually a body of damage, body of crack on the surface, which has to be compatible with the deep beam theory, the bending of the floor, right? So when the bending of the floor, because of that, the cracks are distributed, minor cracks are distributed along the surface of the slab, floor slab, the topping slab, to be compatible with this. So these are the key observations from that. So let's look at the current practice of connecting the floor slabs and reinforced concrete frames. So after Matthew's test, we came up with the interconnection detail, where the precast flooring units were, were rested on the beam, and the topping slab was connecting the precast unit with the beam through this starter bar. And after McPherson's test, we changed that. We recommended that, okay, like every 1 out of 3 or 4 cores in the hollow core slab has to be filled to prepare that end plug, and we add this extra reinforcing steel bar in addition to the steel bar, the starter bar, right? And if you look at the end side detail, how it is connected to the side beam, seismic beam, is after Matthew's test, actually, that was the side floor unit was adjacent to the beam, and then we recommended, okay, we better have a flexible infill part with timber at the base, which is used as a formwork, and then kept it there. So these are the details that are found in most of the hollow core floors, but these in timber infill is used in precast flooring system, and even we use in our test setup there. Now, if you look at the issues with this monolithic connection, The first issue is vertical incompatibility between beams and floors. So this is the beam is trying to bend in double curvature. The floor being stiff isn't trying to follow up. So there is a mismatch, and that's why the linking slab will be subjected to significant damage. Beam strength enhancement due to topping slab participation, which I explained already, so substantial, and that can alter your strength hierarchy and even change your failure mechanism, can force the brittle failure mechanism, can either cause the beam to fail in shear or even the column to fail. And the third is the inevitable tearing damage of topping slab and floor units at the end connection, because we are monolithically connecting through starter bars there, and when beam is trying to elongate, that elongation displacement will have to be accommodated somehow. So there is no way of avoiding that tearing crack, wide crack in that connection. And the fourth is inevitable damage in the linking slab due to deformation demand imposed by elongating beams. And that has been shown in multiple tests like Matthews test, Lindsay, Rennie Lindsay, Cameron McPherson, and Brian Ping, and Lau at the UOA as well. So these result in irreparable damage in moderate to major earthquakes, so not helpful for low damage design. So now let's look at the last slide, how to get around these issues. Performance requirement for force slabs in low damage buildings. What, according to me, the performance requirement is to safely transfer gravity and inertial shear to structural members, to provide diaphragm actions, to avoid potentially fatal free fall caused by unseating, and limit any damage in major earthquakes such that a quick repair is possible and demolition is not needed. Please note the word quick. Okay, so that is the key, because repairability is not achieved if the repair cannot be done reasonably quickly within a time, because otherwise the downtime or business interruption will kill. So a full monolithic connection with the frame all around the perimeter of the floor through topping slab does not satisfy all the above listed performance. Might satisfy some, but that's why I say it is not conducive for low damage building design. Hence, we need to innovate alternate low damage floor frame connection details. I think with that, I end my presentation, and I look forward to questions and interactions. Thank you.
Great, many thanks, Rajesh. It was a really interesting talk. We'll open up for questions now. So maybe questions firstly online, if anyone has any questions. Do we have to unmute them maybe? If I can't hear anyone talking. Do we need to unmute people? If someone is talking, please unmute yourself. I'll start with a question, or maybe I'll hand over to the room. Has anyone got a question in the room here, or a comment? Well, I'll open up with a comment and question. So I thought it was really interesting talk, and you identified a few areas for research. One of which I was wondering though, one question I have around the lump plasticity approach is, with the elongation captured now with lump plasticity, what does this mean for our diaphragm modelling? Because most of the time when we do time history analyses, we assume a rigid diaphragm, but I presume that's not going to work very well. And so what, have there been solutions around that, or?
Yeah, for the diaphragm, I believe the problem lies in the way that we construct rather than that we model. Because if we identify a way to not continuously connect it throughout the perimeter, then we can avoid that part, the plastic hinge part at the end of the beam, right? And not require the floor to follow that deformation. Because the elongation is concentrated on only on the plastic hinge, not in the middle part. And you can transfer the shear through the middle part.
So you would constrain just the middle nodes to, if you
any node in the middle, outside,
put that in your diaphragm. Okay. And the other query I had was, have you looked at using the same model for walls to predict axial elongation of walls?
We have looked at very briefly, but not with this model. We have done just one analysis to see whether it does capture elongation or not. It does. right? No doubt, but we have not verified to the extent. So we know that ability is there, but how accurate it is, I don't know at the moment. So that is a future work. Yeah.
Great. Santiago.
Sorry for being late, but I never expected room E4 to be on the very good.
Okay.
You're saying, if I understood correctly, you want a more flexible connection, less monolithic.
No, because less monolithic doesn't need to be more flexible. It is less monolithic means discrete connection. I'm floating an idea, right? I'm not saying that this is the way to be, but definitely we need to be more innovative and think of alternate ways, right? So, but the problem, we are clear that actually the current way of doing things is the source of the problem. We are probably, in many cases, we are blaming something else for the problem created by this monolithic connection.
Right now, in other countries, you know, well, they use monolithic everything, right?
Yeah.
This slab is monolithic with all the beams.
Yeah.
Right?
Yeah.
That's an alternative, and that seems to work.
No. But if you are looking at like life safety performance, yes, of course, but not for low damage, because if the beams, once the damage happens to floor, it is the most difficult thing to repair. And a lot of demolition that we have gone through is because actually the floor damage is not economic to repair.
I'm talking about cast in place slab.
Yeah.
Take the Nepal. How often did you see in Nepal damaging the floor?
So probably in Nepal, the buildings that you have seen might not have been subjected to, because the acceleration that you noticed like was 1.15 G in Gorkha earthquake in Kathmandu, right? So which is so yeah.
Huge Turkey. So many examples of earthquakes that have affected buildings. Cast in place on the liquid flat as opposed to PreCast.
Yeah.
Very well.
So there was no plastic hinge formed? I didn't visit, but if there is a plastic hinge formed and you have got monolithic connection, how can you say that because the beams is damaged, plastic hinge is formed, something is monolithically connected there, how can it remain intact? Right? So, yeah, so.
Very seldom you see, my experience, very seldom I've seen buildings that are closed down because of this type of damage. When you have
so maybe that is the reason why my paper was not even reviewed by by American journals. So maybe that is probably the belief in the US. I don't know. Look, maybe you might be right, but yeah.
It may very well be. They may see this as a
yeah. So yeah. Yep, maybe. Yeah, maybe our buildings are maybe more ductile than theirs, and there is an evidence, because I was involved in a comparative study between Japan, New Zealand, Europe, and US, right? For the same design parameter, same design demand, we were doing the design and detailing, and that study actually, because Professor Park was leading the New Zealand team, and I was in Japan as a PhD student, and that comparison came. I have the report, like New Zealand is the weakest and most ductile. Right? So for the same scenario. So maybe, I don't know, maybe that might be the reason why it is more of a problem in New Zealand. And we noticed that when we compared the building performance with Japan in Kumamoto earthquake, because our one are much softer and ductile compared to the stiff and strong in Japan.
Okay, yeah, another question.
Very good. I have a question. If the regime or say, after this point, say, for example, it's used as
So the question was, for practitioners, can they? Are there some guidelines about how they should account for this, and should they increase demands and so on?
Yeah. So in a way, like this is in line with some other studies that we are doing. It is system interaction will induce larger forces than what we calculate based on component behavior only. So that is not a new thing actually, because researchers have pointed out, and even in other systems that does work. When you take into account the interaction with floor and gravity frame, your wall is being subjected to higher demand. And it is the same, right? Now, the thing is, how do we quantify it and how do we account for it, right? Because of the different practice in different countries, you know, like if you use their approach of the standard or coded the contribution of the slab, monolithic slab, you will get different values if you use New Zealand approach, European approach, or American approach. And as I said, not all of them can be right. If one is right, other. So the uncertainty that brings is quite substantial. So to be on a safer side, we always have that overstrain factor. But how much is the overstrain factor, system overstrain factor? That is probably need to be relooked at, right, at the moment.
Okay, are there any people online who have a question to ask? If you're trying to ask a question and I can't see it, please use the chat and I'll notice it through the chat. If not, I'll just say any last comments or questions from the room? Okay, then if not, please join me in thanking Professor Rajesh Dhakal for this great presentation and the discussion. Thank you.
Thank you very much.